The purpose of this presentation is to help you to understand the inner workings of soil aerator technology. The technology is designed first of all to not invert the plow layer, but to effectively penetrate it without mixing the various strata of soil biology. By gently and effectively loosening soil, it creates new opportunities for rooting activity and provides for rapid in-soak of water and air exchange. The initial phase of the design is the helixes, which are mirror images from right to left side with adequate space between each position of tine. Now we're going to take a look at the tine body itself and identify its various parts, and how it functions will be evident when we look at the soil and the impact of these design features. The most important part of the tine is actually the compression thrust side of the tine. This is the side which actually is engaging the soil in the forward motion of the machine and the rotation of the shaft, and creates the lateral thrust forces into the soil profile. This beveled edge, which is apparent on all the tines, actually shears the soil as the tine is entering and causing it to split, reducing the amount of rotational thrust that the soil creates on the shaft. It just shears it. This tip of the tine down here is the propulsion face. This contributes to the actual forward rotation of the shaft. As it goes down into the hole, it creates a rotational force. So the back side of the tine, which is not visible to you, over here is actually radiused and tapered so that at a 0 degree of offset on the roller shaft, it actually creates thrust forces on the back side of the tine as well as the front. The other important part of the tine, it's very significant, is the base of the tine, in that the tine blade itself is cast into the base excuse me, at a 5 degree offset. So the tine, even though the roller may be straight, is not just making a clean slice. It's actually twisted, and it goes through a rotation as it moves in and out of the soil profile, creating fracture forces regardless of the offset of the roller. The other aspect of the tine, which is very critical to the success of this tine, is this entry edge. This is a long 45 degree beveled edge, and what it does is part the soil to the compression side of the tine. That is unique and original to the Smart Till tine. Therefore, when this tine is operating, as we'll see in the hole, there is no residual compaction forces left behind the insertion and withdrawal of the tine. And it's because this soil, which if it were parted in the opposite direction would remain undisturbed, as is the case on some competing technologies that look like this tine removes any of the compression forces that have been placed in the soil during the entry phase. Same beveled edge that so effectively parted the soil to the compression thrust side of the tine to accentuate the fracture force is also then, when it comes out of the soil, allowing the side of the hole to actually sharpen the tine. It won't matter how long this tine runs, it will actually get progressively sharper because the soil is actually coming off the side of the tine. That's a function of two things: the angle and the twist of the tine. Now all of this adds up to, as you see in the action video section, the action of the tine and the soil tillage process actually takes place in front of the center line of the shaft. That's when all the work is taking place. Now you can see here, looking from the opposite side of the machine now, we're looking in from the center line of the tool toward the compression thrust side of the tine. This is the actual result in this fairly elastic plastic clay loam soil of northwestern Ohio. This soil has been lifted because it just tends to adhere to the tine. It's that kind of moisture today. But this soil is interesting in that even though it's been lifted like this and worked, you'll see there's amount of fracture that's in here, the soil is actually quite friable. This is not really compacted. The lifting sliding combination action of the tine does a very unique job in terms of soils that would appear to be too wet to till. You can see here another hole. Here is the entry of the tine. The machine was headed in this direction. This is the entry right here. This is the exit over here. You have the very characteristic long engagement of the tine, and this is a function of the shaft speed and therefore the resulting length of time that the tine is actually inserted in the soil. Here again is another piece of soil that has been lifted. You can see the incredible amount of fracture force that's been exerted. The force between these 7.5-inch spacings going all the way over to the other tine mark over here. Now we're going to take a look at the side of the hole, or the tine insertion, where there was no compression forces applied to fracture soil. All this is the evidence of the relief that was caused when the tine entered and moved away. And you can see these fracture lines. What you see in grass pastures and small grains and pasture forage crops in the springtime, this is where you'll first see the new root masses forming up that are characteristically produced by those grasses at that time of the year. They will line themselves right up here at the edge of this in a huge concentration where the air exchange is taking place and the bacteria and fungi are reproducing at a high rate of speed in this freshly opened and tilled zone. And so it promotes huge amounts of root activity in these zones. Same way for this side, but most observable right here.